Hey everyone, welcome to our first lesson in Unit 9. Today we're going to be learning about reaction kinetics and how we can adjust rates of a reaction and what factors contribute to how fast or how slow a reaction is going to happen. We're going to learn about collision theory, and you're going to be able to explain collision theory in terms of criteria that we need in order for an effective collision to occur. You'll also be able to explain three different ways how we can increase or decrease the rate of a chemical reaction. Now, reactions don't necessarily just happen. They happen for a reason, and there's a driving force behind every single reaction. And kinetics is the study of how these reactions occur as far as speed and the process that's followed to get the reaction from reactants to products. So kinetics is a fancy way of saying how the reactions occur and how long they take. Now the mechanism itself is really the pathway or the process that the reaction is going to take. The pathway that it takes from reactants, where we start, to products, where we finish. The steps from reactants to products or along the pathway involve shifting electrons as we break old bonds and we form new bonds. Now, collision theory describes how particles must come in contact with each other in order for an effective collision to occur, in order to get the reaction started. So this theory says that particles of a reactant must collide with each other in order to react. We need a collision to happen. The collisions have to occur with enough energy in order to react. And these molecules have to be oriented properly in order to react. So they have to first collide, they have to have enough energy, and they have to be in the right position in order to react. As long as a collision satisfies each of these three criteria, they're deemed effective collisions, and therefore the reaction can commence. Quick little example here of effective versus an ineffective collision. Considering atom green with atom empty, atom white, whatever, atom beige, whatever you want to call that there, open. It's a closed circle versus an open circle. If we have an effective collision, those two can then combine, reaction can commence, and we end up with a product here. An ineffective collision, we might see the open circle here bounce off of the closed circle or the green circle there. We might not have had enough energy. The orientation might not have been correct. In this case, it looks like they do collide, but one of those other two variables would lead to an ineffective collision, and we would still be left with reactants. So reactions only occur when atoms and molecules effectively collide with another. If we don't have an effective collision, reactions aren't going to happen. Which leads to, well, if we have more collisions, we can have faster reactions, we can increase our reaction rate, and we can decrease the amount of time that it takes for the reaction to happen. And the reverse holds true as well. If there are less collisions, we have a slower reaction, our reaction rate decreases, and the reaction time increases. So we can change, one of the ways we can change how quickly a reaction is happening is how many collisions we allow to happen. There's a couple different ways that we can alter that. So at this point, you should be able to explain collision theory in terms of the criteria, those three criteria that we need for effective collisions: proper energy, proper orientation, and a collision must occur. Hi. Now we'll look at an example reaction mechanism where we have hydrogen plus iodine yields 2 hydrogen iodine. This doesn't just happen in one step. There are multiple steps that happen. First step that happens, the bonds in hydrogen have to be broken, so we're left with 2 hydrogen atoms. And in order to break a bond, we have to absorb energy. So we break bonds, we absorb energy. We form bonds, we release energy. Same thing has to happen for iodine. We have to break the bonds between the 2 iodine atoms in the molecule, and we're left with 2 iodine atoms. Now, these individual atoms can recombine in their 1-to-1 ratio to form hydrogen iodide. This hydrogen would rather bond to iodine than itself, so the atoms rearrange themselves so that this can happen. When we form the new bonds in hydrogen iodide, 2 of them in fact, that new bond that forms releases energy. Now, looking at this mechanism, at least in a similar example, we're going to apply this to a potential energy diagram, which we will cover in our next topic. So the 2 hydrogen and 2 iodine that are formed in our first steps, 1 and 2, are what we call an intermediate, or it's what we call the activated complex. And the activated complex is at the top of our graph here. And if we meet the criteria for an effective collision, then we can have these 2 bond with each other to end up with 2 nitrogen oxide. But we had to break the bonds here first in N2 and O2 in order to form the intermediate, or what we call the activated complex. And that's going to require energy in the form of what we refer to as activation energy in order to actually break those bonds. And if we don't have enough activation energy, then the reaction can't get started because the molecules N2 and O2 will not have been broken. So a mechanism is like taking different roads to a different place. Depending on the road that you take, it might take you a different amount of time to get to your destination. Think about taking an alternate path to class. There is a direct route. There might be more of a roundabout way. There's probably multiple ways that you could get home from school. One might be more of a direct route. One might be a slower route. Maybe you're going to take every side road on your way home as opposed to just taking a main road straight down. You'd obviously get to your home at some point, but one's going to take longer than the other. And in certain scenarios, increasing the time it takes for a reaction to happen might be desirable, but we could also use the mechanism to shorten the time it takes for the reaction to occur. The only way we can figure out what the mechanism is to do an experiment. And there's a certain step here which we call the rate determining step, and that's what's going to determine how fast a reaction can occur. And it can only occur as fast as the slowest step. Such as if you were walking from band to chemistry and you had to make a locker stop, the locker stop is going to be your slowest step. You're not going to be gaining any more distance towards your destination, and time's going to keep ticking away. And you can't get there any faster than you can get past your locker. That's what's going to slow you down. That's what's going to determine your rate. It's how much time you spend at your locker. So we can only proceed as fast as our slowest step, and that's known as the rate determining step. So there are different ways that we can affect the rate of a reaction. Generally, there's 2 ways. We can either change the mechanism or we can change the number of collisions. Let's take a look first at changing the mechanism. A catalyst is a chemical that can be added to a reaction that changes at least 1, sometimes more steps in the mechanism itself. Catalysts make the reaction proceed faster. Could be by shortening a step, removing a step, but it's going to alter one of the steps of that mechanism. Catalysts do not get consumed by the reaction. They can be reused over and over again. And it's kind of like finding a shortcut, either going to class or going home, or if you're driving somewhere. The shortcut gets you to the destination faster. The shortcut will still be there to be used over and over again as you go back and forth to school or back and forth to class, kind of like cutting through the courtyard to the library. Inhibitors are going to alter our mechanism by increasing the amount of time that it takes for the reaction to occur. So it's going to adjust the mechanism by adding a step or more to the mechanism to slow down the rate of the reaction. So it's going to decrease the speed and will usually increase the activation energy. It's going to require more energy from each molecule in order for the reaction to actually get started. Inhibitors like catalysts are also not consumed. kind of like encountering a roadblock or maybe some construction, closed road when you're driving, or maybe an accident in the hallway when you're moving between classes that you have to kind of detour and go around. It's going to use more gas or take longer to get to your destination if you have to walk outside to get to class, go through a parking lot, go around the road detour, down a different side street and get back on your path. But it's still going to be there after you go through it. The other way that we can affect the rate of the reaction is by changing the effect of collisions. Now, types of reactants are greatly going to influence the speed of the reaction. Ionic reactions tend to occur the fastest, especially if they are already in solution and ionic bonds are already broken by the solvent. Covalent reactions tend to occur pretty slowly, and gases will proceed more quickly than liquids, which proceed more quickly than solids. We have more space between molecules. We can therefore have more effective collisions as particles have more freedom to move around and more space in between. Temperature will change the amount of effective collisions by affecting the speed of the colliding particles. If we increase temperature, particles will move faster. We will have more effective collisions with higher energy because of the increased temperature. So increasing temperature almost always increases reaction rate. And the opposite will hold true as well. Concentration also directly affects the number of effective collisions. If we have more particles around, they're more likely to hit each other because there's more available. More cars on the road, you're more likely to get into an accident, you're more likely to collide with one of them. If you think about that in the reverse, if there were never any cars on the road, you would never get into a collision or an accident with another car. Increasing concentration increases reaction rate. In gases, this is the same as increasing pressure, since the molecule will get squeezed closer together with increasing pressure. So if we increase pressure for gas, we are also increasing concentration by forcing those molecules closer together. Surface area directly affects the number of effective collisions. If we increase the surface area of reactants, it's going to increase the frequency of effective collisions. That's why we crush our reactants when we use them in an experiment. We create more surface area by crushing and grinding using a mortar and pestle, and therefore we can have more effective collisions and allow our reaction to occur faster. So factors that will increase the reaction rate: high temperature, high surface area, high concentration, a presence of a catalyst, and the nature of reactants. Ionic substances will react faster compared to gases, liquids, and solids. And that's from fastest to slowest. At this point, it should be able to explain 3 different ways to increase the rate of a chemical reaction. Make sure you guys record any questions that you have. Make sure you bring them up when I see you in class next. Have a great day.